Hi, my name is Kruthik Alapati, and this is my presentation on Lab 4 circuits. The objective of this lab was to use principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the values of convectional current and potential differences, and examine the behavior of ohmic resistors and capacitors. So a preview of the results were that for part 1, the experimental result was the same as the predicted result, and for part 2, the experimental result was lower than the expected result. The concepts and formulas that we use in this lab are conservation of energy and charge, Kirchhoff's circuit laws, Ohm's law, steady state of circuits, time dependence and resistor capacitor circuits, the capacitance of a capacitor, and series versus parallel circuits. And you can see the equations to the right here. In this experiment, the system is the circuit, the surroundings are the universe surrounding the circuit, and the model that we used for this experiment was the PhET online circuit simulator, and the assumptions that we had were that there were no resistance in the wires and no resistance in the ammeter. So for part 1 of the experiment, the setup was that there were two 1.5 volt batteries, one 47 ohm resistor and one 100 ohm resistor, and two ammeters. So the results that I predicted using Ohm's law was 0.0204 amps, and the experimental result was 0.02 amps. The reversal of the ammeter negated the measured current, and it was negative 0.02 amps. The next setup for part 1 was placing one ammeter with one voltmeter. The predicted result was a potential difference of 3 volts and no current, as the circuit is not closed. The experimental result was the same as the predicted result, and you can see that in the diagram to the right. So for the next section of the experiment, I set the voltmeter at different parts in the circuit, as you can see in the top right diagram, and then I measured the potential differences across these different points. So from A to B it was from A to B it was 3 volts, B to C was 0 volts, C to D was negative 0.96, D to E was 0, E to F was negative 2.04, and then the rest were 0. And since the sum of all parts is 0, the loop still holds true. And then I plotted these across the circuit diagram in the bottom right diagram, as you can see. So the next part, I set up a 100 ohm resistor parallel to an ammeter, and the result was that the overall current increases to 0.06 amps as the circuit splits. So now there's a resistance-free path, which allows for an increase in the current of the circuit after the split, and the experiment supports the node rule. The resistance calculations that I did resulted in the 47 ohm resistor having 48 ohms and the 100 one having 102, and the wire and ammeter having 0. So for part 2 of the experiment, the setup was 10 ohm and 20 ohm light bulbs for two separate scenarios, a 200 millifarad capacitor and a 9 volt light bulb. The observations I made with the experiment were that the battery charged the capacitor after connecting the battery until the light stopped and the current dropped to 0. And when the capacitor was connected to the light bulb directly, the capacitor was discharged and the light bulb lit up again until it abruptly stopped and the current also dropped to 0. So the results were that when the battery was connected to the 10 ohm light bulb, the charging time was 15.62 seconds and the discharge time was 15.77 seconds. And for the 20 ohm light bulb, it was 27.62 seconds and 27.67 seconds. I then did the next part of the experiment, which was setting up a 30 ohm light bulb with the same 30 ohm resistant light bulb with the same setup, and a voltmeter across the capacitor. And then I recorded the voltage every 1 second from 0 to 20 seconds. Then by deriving the linearized form of the energy conservation equation, we can determine the RC value, and you can see the linearized form below. The expected RC was 30 ohms times 0.2 Faraday, which was 6 RC value, and the slope of the linearized equation is negative 0.1733. So we can calculate the RC by taking negative 1 over the slope, which gives us 5.77. The calculated percent error was 3.83%, and this probably is due to human error in measuring time, since there's no error in the online simulation, because an ideal circuit has negligible resistance in the ammeters and wires. So the current and voltage along a circuit are time dependent and have an exponential relationship with time, and the node and loop rule hold true, as they can be used to calculate changes along circuits. If this lab was done in real life and an actual ammeter was used instead of a simulated one, likely the ammeters and wires in real life don't have negligible resistances, so the measured voltage and current would be lower than in an online simulation. And if we were doing this experiment in real life and used a real battery to charge the capacitor doesn't have negligible resistance, and on top of that, the online model doesn't account for non-immediate charge cycles. So due to these two things, the measured time would be longer than the predicted time in the lab.